All right. Oops. So I haven't really received any emails or questions other than the ones I've responded to in email. The only trend I've really picked up on is with the WebAssign, when you use atomic weights, only use 1 decimal point precision. It says in the prompts there's a reason for this. If you use 2, 3, 4 decimal points precision, sometimes what you'll end up getting is what's referred to as rounding errors. So basically, your number's so precise it gives you a slightly different answer than what the key was calculating. So for exams, by all means, use whatever number of decimal points you want to use. By the way, like breaking over a sprain in my back. Use any number of decimal points you want to use, but for the homework, stick to 1 decimal point. And when it comes to calculating significant figures for your final answer, use the numbers that are given in the problem. Don't work on the atomic weight. Now, another common thing I'm seeing on the homework, just been a handful, but in case y'all haven't started it, the homework does require you to report the appropriate number of significant figures. Don't burn through your submissions trying to guess what's wrong. If you've entered the answer 2 or 3 times, you're still getting the same answer and it's still counting it wrong, shoot me an email. I can see on my end what your attempts were and see if you're actually getting the wrong answer or if this is just a situation where you've got the wrong sig figs or something like that. So again, don't burn through your submissions, especially with the first one. Usually the first question on these homework assignments, pretty straightforward. You can probably even do it without a calculator. You should be getting nice clean numbers. If you're not getting nice clean numbers or it's still marking it wrong even though you got a clean number, odds are that's a formatting issue. It's not really an issue of what you've done. And just got a question. So let's say you had something like 60.55 for your atomic weight. Do you round or drop? Do the rounding. So anything 5 or higher rounds up, anything less than 5 rounds down. We're not going to do the engineering rounding where it's like even numbers round up, odd numbers round down, something like that. Just your normal chemistry rounding rules. And I'm also probably going to try to figure out today, well, during the live stream, there's something weird with the gradebook, like it's gotten rid of some of my columns. But oh, actually, I have questions. Is an option you can set for us to tell us the significant things are what is wrong? Not really. As far as more attempts, I don't give more attempts. Big thing is each individual homework set by itself, if you really work it out, is less than 0.01% of the grade. Um, Again, this is kind of encouraging you not to burn through your submissions. But again, if you're curious if it's sig figs, just shoot me an email. I can see all your answers on my side, everything you've submitted, and I can tell you from the ballpark. And definitely, if you've got the right answer, it's just sig figs. I'll tell you, you've got the right answer. It's just sig figs. Or sometimes we do get a few problems where like there's little minutia depending on where you round it. Particularly as we get later in the semester and the problems get a bit more involved. I can tell you what the right answer is if I'm pretty sure you're doing it right. I think because each problem is worth 1 point, I think there's a total of 650 points in a semester. And keep in mind, like some problems are worth multiple points. So if you missed 5 problems out of 650, it's not going to really affect your grade. And again, keep in mind the homework's 2.5%, so we don't really have to like. It's not make or break if you don't get the homework perfect. If you really need that half of the point at the end of the semester, I can probably find a way to give it to you. Sure. Which homework? Which problems in particular? Like, so which homework and which problems? so test one, colligative properties moderate, molecular weight from osmotic pressure, and concentrations hard. All right, so let me bring that homework set up. Where's my marker? There you are. Actually, sig figs aren't that bad, and this card also. So the thing we had to breach for test one is kind of like reviewing Chem 1 as well as teaching you the new material. Let's see here. Test 1, colligative properties moderate. Why does it never show it to you in alphabetical order? It looks like I'm going to need the tables off of excuse me. Need to download the tables of physical properties too. Almost there. All right, so for the first problem on test 1, colligative properties moderate. Using only 1 decimal for atomic weights, what is the change in the boiling point of cyclohexane if 1.93 grams of C3H7OH are dissolved in 2.5 kilograms of cyclohexane? So the formula for this is delta T equals K I little m. And let's see here. We've got cyclohexane. We've got 1.93 grams of C3H7OH. This is dissolved in 0.250 kilograms of the cyclohexane. And we're looking the boiling point. So here we want the K sub B. And it tells you in the problem, the Van 't Hoff factor, the I is just 1. So we have I, 1.00, and we've got the KB for cyclohexane here is 2.79. The M here is the molality, so to figure out the molality, we have our 1.93 grams of C3H7OH times 1 mole. The atomic weight here is we got 3 times 12 plus 8 for the hydrogen plus 16 gives us 60 grams per mole. And we want to divide that by the 0.250 kilograms. You still see that? 0.250 kilograms. So if I plug that into Excel, I get 1.93 that divided by 4. I get a molality of 0.008042 grams. So now I'm just going to plug that M back into this equation. Oh, actually, no, that's not correct. Divided by 0.25, sorry. I was curious why the number was so small. Okay, so the molality here, 0.28667, so forth. If you plug that in, so that number times 1 times 2.79 will give you a delta T of 0.35898. Given the problem, it gives you 3 sig figs for this number, 3 sig figs for this number, so we're going to count out 1, 2, 3. So our boiling point change here is 0.360 degrees. If I plug that in, counts that as correct. So in terms of needing to additional problems to learn the concepts, actually if you go to the course website under lessons 1, there's also additional study packets and problems. So even though you've exhausted your attempts, those study packets are kind of like extra homework that you can do as optional. Generally what we use for our rule do for significant figures, if it's a physical constant like we have in the tables, those don't contribute towards significant figures. If it's a conversion factor like molecular weight, it doesn't contribute to significant figures. Most of what we're going to do this semester is multiplication and division. So it's going to be limited by the sig figs of the least significant number given in the problem. But again, conversion factors and physical constants, we treat those as infinitely precise even if they're not, because we don't necessarily, well, mostly because they are physical constants and they shouldn't be changing our precision. So if KB, for whatever reason, had one significant figure, you would just ignore it as having one significant figure. And you would just treat it as an infinitely precise number. Where are you? There you are. Now the rest of the problems in this set are solved the exact same way. So what's the change in the boiling point of acetic acid? You would go to that table. It gives you the weights, gives you the Van Hoff factors. The bigger challenge with this is keep in mind boiling point is KB, freezing point is KF. So yeah, make sure you're looking at the right values of K. For the molecular weight from osmotic pressure. This one's a bit more challenging. So for osmotic pressure, pi equals trim. So pi here is the osmotic pressure in kilopascals. Yep. T here is the temperature in Kelvin. R is your ideal gas constant, 0.008314. Actually, no, it gives it to you. It tells you R is 8.314. Sorry, I tried to do that conversion in my head. I is your Van Hoff. M here is your molarity. So the thing to remember about molarity is defined as moles per unit volume. And moles here are your grams divided by molecular weight. So there's a few approaches to this. I would recommend the keep it simple approach. In fact, this is what the problem tries to walk you through, is kind of like walk you through it. So the first thing it asks you for is molarity, which is this part here. So if we rearrange this formula, molarity equals the osmotic pressure over the temperature times the gas constant times R. And again, keep in mind temperature here needs to be in Kelvin. So bring up Excel. So it's that 201.6 kPa divided by the temperature, which is 18 plus 273 times the Van Hoff factor, which is 1, times R, which is 8.314. So here you're going to get the molarity as 0.83327. 08, sorry. And if we look at the tables of values, the Van Hoff factor should have a 1.00 in it, but everything else here is given to you to 3 significant figures. The osmotic pressure is in 4. So we're going to truncate to 3 significant figures. So our molarity here is 0.0833. Now to figure out the molecular weight, we've got molarity equals moles over volume. So if we take our molarity, multiply by volume, this will give us our moles. And we know that our moles are the grams divided by the molecular weight. So if we rearrange, we get that the molecular weight is just the grams divided by the molarity times volume. And so it gives you that you had 5 grams. Your molarity is at 0.083327, and your volume here is 1 liter. Oh, mercifully, it doesn't actually convert that. So here you get the molecular weight to be 60.0. And we're going to carry on that tradition of 3 sig figs. And I will give you a hint, for the osmotic pressure ones, they're all 3 significant figures. So the homework we're doing right now is the molecular weight from osmotic pressure. Now, a few things to keep in mind when you do these. First of all, molecular weights, particularly with light molecules, end up being pretty simple integers, so you should be getting something close to an integer. On top of that, molecular weights all have to be greater than 1. So if you end up getting a molecular weight of like point something, that's physically impossible. Hydrogen which weighs 1 AMU, so there's no way to get anything that weighs less than 1. And you're probably not looking at monatomic hydrogen dissolved in water. But basically, it walks you through it. Isolate the molarity first. From the molarity, figure out your moles, and divide your grams by moles to get your molecular weight. Also keep in mind with these discussions, there's about a 30 to 45 second lag. So I'll try to keep on top of the chat, but there is a lag between when I say something and when it actually shows up to you, and when you say something and it shows up on my end. So I'll give you about a minute to catch up. Yeah, this is what I say, like, don't burn through your submissions. Like, if you're doing it like 2 or 3 times, let me know. Again, I can see it on my end if it's sig figs. Because, I mean, it's reassuring to know, like, you've done it right. You clearly understood the concept. It's just this little minutia. I mean, it's something we kind of have to get students back into for Chem 2 is remembering, like, sig figs are a thing. Now, I'm saying that now. Halfway through the semester, we're going to start solving quadratics and start solving logarithms. At that point, it's all 3 sig figs. But for now, we're still doing it. All right, test 2, 152, test 1, concentration's hard. So I'm going to go out here and give you some inside information on these types of problems. We are required to teach you how to do this. This will be a multiple choice question on the homework, on the exam. It is a single multiple choice question. So it asks, what is the molality of a 3.90 molarity? What is the molality? Oh, it's asking for mass fraction. So we have a 3.90 mole Na plus solution. And what we want to know is the mass fraction, the grams per gram of sodium plus. Now, I really don't like these problems because there are a ton of assumptions built into them. So, a few guidelines. Usually molarity and molality are the same number, and they're a lot smaller than the mass fraction by about 100 to 1,000. So what we expect is our molarity to be 100 or 1,000 times smaller than that number. So I got another question. I'll answer that after I answer the question on how to do these. So in order to solve these, what I tell students is these numbers, the concentrations and the mass fractions, don't depend on how much we have. So step one is we're going to assume we have 1 of whatever unit is in the denominator we're starting with. So we're given 3.99 mole. So we're going to assume 1 kilogram of solvent. Now, do we actually have 1 kilogram of solvent? No. But this makes the math really easy for converting between molality and the weight fraction. So the molality is defined as moles of solution per kilogram of solvent. So if we have 1 kilogram of solvent, then that tells us, based on this, we also have 3.09 moles of Na+. Now, what we want to get is grams of sodium per grams of solution. So our grams of solution is just our grams of sodium plus our grams of solvent. Make sure you can still see that. And our grams of sodium is just our moles of sodium times the molecular weight of sodium. So in this case, 23 grams per mole. Now, I assumed 1 kilogram of solvent. So I've got 1,000 grams of solvent. And let's see what 3.9 times 23 is. And I've got 89.7 grams of, actually no, sorry, I got this backwards. The weight fraction is going to be a lot less. I don't know, let's figure it out. So my grams of solution here is 1,089.7, and I've got 89.7 grams of sodium. So by definition, the weight fraction is just our grams of sodium divided by our grams of solution. And in this case, it's the 89.7 divided by the 1,089.7, we get 0.0823. So I'm sorry, it's actually smaller by about 100 or 1,000. So that's kind of how you approach these problems. I would really recommend the videos I have online. I've tried to work a few of these examples. But basically, you take whatever unit you're given and you assume 1 of whatever's in the denominator. So if you start with molality, you assume you have 1 kilogram. If you're given weight fraction, you assume 1 gram of solution. If you have molarity, you assume you have 1 liter of solution. There are 3 formulas you use to convert from one unit to the other. So the grams of solution is going to be the grams of solute plus the grams of solvent. The grams of solute equals the moles of solute times its molecular weight. And the last one that we didn't use for this problem is that the density of the solution is the grams of the solution divided by the volume of the solution. So how do you solve changes in boiling and freezing when the solute is volatile? So just to figure out the boiling and freezing point changes, it's the delta T equals K I M. If it's boiling, that's the same thing as, so if it's boiling, it'll be KB. If it's freezing or melting, it'll be KF. And as far as the values for KB and KF, they are tabulated. Actually, if you go to the lessons 1, there's the test 1 formula sheet that's available for you. That's also going to be available for you on the exam. You can see all these tabulated values of KB and KF. Strictly for non-volatile. Okay, so the textbook's a little misleading in that regard. You can't, if it's a liquid, it's going to be volatile. The difference between volatile and non-volatile is kind of a fine line. Oh, it means a volatile solute. Okay. So in this case, let me go back to the example. Polluted properties moderate. So in this case, we're just going to treat the compound. So in this case, the propanol, the water is having basically very low vapor pressures relative to the solvent. So this is just kind of a simple approximation that we're making. It's fine what we're doing. They are technically correct. You should be limiting yourself to salts rather than liquids in this case, particularly liquids that may have a relatively high volatile pressure. We're not going to worry about that in this course. So yes, a purist would say that you need to stick to salts. Honestly, the propanol and the water, what they're dissolved in, have substantially higher vapor pressures. And we're also using very small amounts, so this formula can still be applied. We're working with such small amounts that we can effectively treat them as they are, as if they are non-volatile. So if we had like a 25% mixture or something like that, where we had a really high amount of material, like high number of moles dissolved in it, we would start using other approximations. WW nomenclature. So I have read a lot of textbooks on how to do weight fraction, and the thing I've never seen is an abbreviation for weight fraction. So molality is easy. It's a lowercase m. I usually put a strong hook on it because I'm left-handed. We've got big M for molarity. But weight fraction or mass fraction, I've never seen a textbook give a consistent symbol for this. So the two I've seen are G over G and W over W. And what these represent are grams of the solute over grams of the solution, or the weight of the solute over the weight of solution. This is more for the English units, because in English there is a distinction between weight and mass. This is more metric. But when I was being taught weight fraction, this is what we were taught was grams per gram. And so the reason why it needs to be specified grams per gram is that technically weight fraction is unitless. And this is a really bad idea in the literature to say that this is a unitless number. Because the thing is, let's say the weight fraction of oxygen in CH2O is, and I'll make this up, 0.250. And I say that's a unitless number. So if I multiply this by 1.6 grams of CH2O, in principle, I can get the grams of oxygen in this. But I could also multiply it by 1.6 grams of CH4. There's nothing to stop me from doing this unit-wise. The other thing is I don't end up with what I want, which is grams of oxygen. So the unitless argument says it's grams per grams, and therefore it's unitless. There is, my school of thought that I was raised in, is that this isn't a unitless number. It's defined as grams of oxygen per grams of CH2O. And so the only way to get the grams of CH2 off the bottom is to multiply by grams of CH2O. I can only multiply by grams of whatever I'm in. And this will also finish me off with the correct units of grams of oxygen, which is what I'm going for. But again, I've never seen a textbook consistently give a unit here to show what the symbol is. So my chemical engineering background, this is what we use, G over G or W over W. Again, this was more for English units when you were working with like pounds or tons or things like this. This was reserved more for metric, where mass and weight are synonymous. Here, mass and weight are not synonymous. WW would be independent of the molarity because it's based on the molecule instead of the solution, right? While G per G is specific to the action mixture. So G and G and WW are going to act the same. We're also not going to work with W per W. I may have it in the slides, but it really should be G per G. But the weight fraction does depend on the molarity, because the molarity is the moles per volume, and the volume is the density divided by the mass of the solution. So molarity here is moles over the density times the mass of the solution. The moles here will connect to the mass of solute. So if we rearrange this, we get in. There's a way to rearrange this to get the formula, but they are connected. So the way you can think about it as crudely all of these. So molarity, molality, and mass fraction are all the amount of solute over the amount of solution or solvent. So all of these reflect a concentration, they just reflect the concentration differently. And because they are all reflective of a concentration, if you increase this one, you expect the other two to increase, because the only way to increase the molality is to increase the amount of solute that's dissolved. Well, that's going to increase the molality because you've increased the moles that are dissolved. And it's going to increase the weight fraction because you've increased the amount that's dissolved. But both G and G and WW both depend on the concentrations. The reason why I say W over W is the weight and the mass don't necessarily connect. It's a fluke of English units. So what you weigh here on Earth is not the same as what you weigh on the moon. So what you have to do is you take any weight on Earth. So let's say your weight in pounds. LBS. And you divide it by 1 over 32.1 feet per second squared. That will give you the pound mass that you actually have. So your pound mass doesn't depend on what planet you're on. But the thing is that if we take our weights, W and W, and we divide both of them by 132.1, so our weight of solute and our weight of solution, divide them both by 1 over 32.1, this will get us to grams per gram. But the 1 over 32 cancels out on top and bottom. So WW is going to act the same as G and G, but with engineering, you have to be a little bit more precise to say that if you're working in pounds, you have to specify, is it pound weight or is it pound mass? Because they're not the same number, but because you're dividing both weights by each other, any conversion between pound weight and pound mass will get you back to the exact same number. It's a nuance, it's nitpicky. This is why we work in metric. Yeah, I know there's probably a little bit more in-depth explanation than you ever really need in a chemistry course at this level, but I try to tell you the truth. Um, I can do teams. The two issues I have with doing teams is that it also typically ends up one, I can't really record it. There's issues with student anonymity when we do teams. The second is that Teams does really low resolution videos, so to work something like this, it might be a little too blurry for you to see. Typically, most of the instructors I talk to work it out on the screen. So, particularly, I have a STEM hour on Wednesday mornings. That's on Team, so if you want to show up there, we can talk one on one in one of the breakout sessions. But my reason for picking the YouTube platform is I can record this. It shows all your chats off to the side in real time, so people can come back later and watch the videos. Whereas with Teams, I mean, you can record videos on Teams, but there's a lot of issues with one, it's really low quality video, and two, with Teams, there are some issues about anonymity. Like sometimes Teams can record way more information than you should be allowed to put on the internet. Let me phrase that. It's impossible to be anonymous on Teams. It's very possible to be anonymous on YouTube. I mean, you're always free to try to schedule time outside of office hours. Just afternoon, my schedule gets a bit more volatile. And yeah, I would say the easiest way to do the in person would be on Wednesday mornings for the STEM hour. I think it's at 9 a.m. It's a little early. Let me check. I should check because I have to show up this week. And those are much more one on one. Yep, 9 a.m. Wednesday morning. The shame was they didn't tell us too late we could go back to in person office hours. I don't know if that applies this summer or not, but that's definitely an option that we're going to start implementing this fall so we can get the in person one on one again. Didn't do any good this summer, but most of the time no one shows up to my STEM hour. So if you want to show up, feel free to it. I mean, this is a resource you're paying for, so by all means, like utilize the instructor. Like, not really. So, WebAssign's funky with copyright issues. So the homework you're doing are the homeworks I've had to develop. So we used to work with Burge's Ab's first textbook, and the thing is that if you use any of the textbook questions, first of all, it presupposes the textbook questions are good. That's a big presupposition. The second is that if we tie it to a textbook, the textbook owns the questions. And so if we switch textbooks, we no longer are allowed to use these problems. And this creates issues whenever we update the textbook. Now, we don't do it very often, but when we do, it basically means we have to completely recreate the course. So the reason why these aren't tied to a textbook is they're not textbook questions. They're questions I developed. And they're meant to be so that if we change textbooks or you use a different textbook, or we've definitely had publishers yank us around and say, hey, we want a whole bunch of money now for you to use our textbooks. The students don't have to worry about the cost, and we don't really have to worry about textbooks changing editions and things like that. Now you're kind of seeing on your end that because it's not tied to a textbook, it doesn't really tie to a section in the book. That said, I try to keep the notes sufficient for helping, so my PowerPoint sufficient for you being able to do the homework. Actually, this morning I reloaded the notes. I forgot that there was an update in the notes. So if you go to the course website now, there's a lot more information on functional groups, intermolecular forces, and things like that. It's a lot more spelled out. So as far as a good way to do that, I would say go to the, if you're a read write learner, you prefer like PowerPoints, go to the PowerPoints, download those. Um, look at, see what the homework topics are, read that section of the notes. See if you can do the practice problems in the packets if you just want a low weight, zero cost question to ask, because the packets also have their solutions. So you can see if you're doing it right. But if you want to do the homework, do the homework. If you're still not quite getting it, go to the book, look up the index, and find where that particular question is in the index. If you're an auditory learner, there's the online videos. They're basically mini lectures, about 4 to 6 minutes on average. And you can go to those and basically see what the homework question is, go look up that topic in the video, watch the video, and start working the problems. I prefer to read textbooks personally. I'm trying to think. I think for right now, it's a section in the book. They're trying to remember for this course if there's like a weird jumping around. I know there is for organic, but I think for the most part we follow the book in an order. So if you go to the course website and under that Lessons 1 ribbon, or underneath that Lessons 1 folder, towards the top you're going to see one that says Properties of Solids, Liquids, Gas, Liquids, and Phase Diagrams. PowerPoint opens in current folder. That's everything for test 1. Actually opening it right now. So I can bring you down the desktop really quick. Stop it. Here we go. So we've got review phases of matter, intermolecular forces, functional groups, surface tension, cohesion, adhesion, viscosity, Clausius-Clapeyron equation, properties of solids, densities of solids based on unit cells, phase diagrams. For the phase diagrams, you don't need to know the calculus. I think it says that in the notes. This is mostly to explain where Clausius-Clapeyron comes from. What else? Different types of solutions, melting freezing point changes, heats of dissolution, converting between units. That looks like Raoult's law. Yep. Explanations where the Van Hoff factor comes from. There are some worked examples in here. Osmotic pressure, electrolytes, And colloids, you just need to know a couple examples. We don't really go into any depth on colloids. So if you go to, so you're allowed to use your notes on the exam. So technically you don't have to memorize any formulas. If you have notes with all the formulas on them, you can use those. In a seated lecture, I would make you memorize Clause's Clapeyron and osmotic pressure, freezing point, boiling point changes, and there's a couple other. Which one am I forgetting? Oh, Raoult's law. But because this is an open notes exam, you're free to write down all the formulas as long as, and actually it tells you on the study guide, formulas to memorize. Enthalpy form of Clause's Clapeyron, boiling point, freezing point change, Raoult's law, osmotic pressure, and to be familiar with packing density formulas for the crystal structures. If you look at the Formula One sheet for the exam, those are the formulas I'm going to give you. But again, it's an open notes exam. So I would say if you want to write down your notes, all the formulas, you're free to do it. As far as it giving you a gray screen, try a different browser. It should also, it may be trying to make you preview it. So you may have to use a different browser. Because sometimes it will do the gray screen, particularly this is a 10 megabyte PowerPoint because of all the diagrams and figures that are in it. So it may just be having trouble letting you do a preview. The standard cubic crystal face center, you need to know how to identify them, and you need to know which formula corresponds to which packing density. But those formulas will be provided to you on the formula, the exam 1 formula sheet. It just doesn't specify which one's which. But if you want to, in your notes, you can go ahead and download that formula sheet, identify which formula is which, and then just make a note of it. But we don't go beyond face-centered. We don't go beyond primitive, BCC, and FCC. There's just no point. Honestly, the packing density formulas we have aren't particularly useful. They make a ton of assumptions. So it's mostly just kind of introducing you to crystal structures and how you could infer density from those crystal structures. I would say this upcoming exam will be the broadest exam you take. It's got a lot of free response questions, but they're kind of like here or there. Yes, so to get from the atomic radius to density. So if you go to, again, you're going to see one that says test 1 formula sheet. There's 3 formulas. It takes you from the atomic radius and the molecular weight all the way to the density. So the density is on the left side. The only thing you have to plug into that is the atomic radius, and I think it even it gives you that formula in nanometers, which is the typical unit of measurement for the atoms, and the molecular weight of the atom that's being used. Now, if you're asking, like, do you need to know any crystal structures beyond FCC, BCC, and P? No. There's lots of them. There's diamond crystal structure, there's sodium chloride, there's lots of them. Yeah, it's the fact that you've got to kind of like do 2 hypotenuses to get through BCC. It's a lot of work, and it's a lot of work for a formula that's like right half the time. I mean, I think it's an interesting exercise, but I don't think it's necessarily a practical outcome. It's something that translates better to a seated course. What I really wish we could go into on crystals, which I think is far more interesting, but unfortunately outside the scope, is this concept of coordination numbers. So in a BCC crystal, we have actually the center atom is connected to 8, actually has a coordination number of 8. And it's weird to explain because if you look at something that takes that type of structure, so if you had, let's say, actually sodium chloride is a great example of this. So with sodium chloride, you've got the chlorine cations, and around it, you got the sodium cations. So each chlorine atom has a coordination number of 2, 4, 6. But when we write the formula, it's NaCl. So each of these represent basically a sixth of a bond. So I think that's more interesting, is going into the idea of the properties of solids themselves, but we just don't cover them in this course. And honestly, it is a little bit better left for material science course, but taught. So by doggies, we're just going to keep teaching it. The tetra, the octa, and the cubic holes. You don't need to know anything about it. We don't go into defects. Um, Functional groups are a good one. That's part of the reason. So there's 2 reasons I introduced functional groups at the start of this course. Is one, it is kind of set up for the organic courses. Because the first thing you talk about in organic are functional groups, and they do have a ton of information embedded in them. Less so our intermolecular forces. They do show up, but if I'm being honest, we don't talk about them terribly much. But definitely the functional groups will show up. And the rates of reactions, you'll start seeing references to unimolecular and bimolecular reaction mechanisms. The mechanisms come up a lot because they affect the rate laws, so some of the rate stuff's going to show up as well. Organic is kind of the first specialty in chemistry, so we're going to try to kind of build off of Gen Chem 1 and 2. But one of the nice things about functional groups is they eliminate the need to actually do Lewis theory. They're kind of a shortcut for Lewis theory. And yeah, so that's why we're introducing them to now to say, like, you can go back and you can draw the list structures from scratch. There's nothing wrong with that. It's just highly inefficient. Functional groups, you're seeing that now. Functional groups can quickly tell you what the IMFs are. They can also tell you geometries. They can tell you reactivities. If you know all the functional groups in a molecule, you know what class a molecule is. Is an aldehyde, ketone, carboxylic acid, alkene, alkyne. All of that information is wrapped up in these functional groups. So rate functions, I wish we could teach it that way. So reaction rate we represent as R. So let's say we have A plus B goes to C. And if we have the assumption that this is literally what happens, A and B come together to make C, we can say the rate of reaction is some constant. We're going to say constant really depends on temperature times the concentration of A times the concentration of B. And depending on what we're looking at, so if we're looking at the rate of A, we're consuming A. So the rate of any species I, so A, B, or C, it's just its reaction coefficient times the standard rate. But the rate here really is D, well, written here it's dx dt, but here it's dA, concentration of A, dt. We would love to be able to talk about reaction rates in terms of calculus because it makes solving them a lot easier. But we don't require Calc 1 and Calc 2 as prereqs for Chemistry 2 at Wake Tech, and so we can't say that this is really a derivative. We do the thing that always makes me cry inside where we say that, well, really it's delta A over delta T. That's not true. It's a first derivative. But the rate is the change in concentration over time. So it does meet the definition of a derivative, and in reality it is a derivative, but because we don't require Calc 2 for the course, we can't talk about them like they're derivatives. And particularly if you've gone beyond Calc 2, if you've done Calc 3, X here is the extent of reaction. And the concentration of any compound is its starting concentration minus its reaction coefficient times the extent of reaction. So we can convert any rate law into an ODE using extent of reaction. That's something that's lost, though, if you're not looking at it in terms of calculus. Now, whether or not you can solve that ODE is a matter of debate, but the fact is you can turn it into an ODE, which is a lot nicer to work with than a PDE. Which I guess it should qualify. ODE is ordinary differential equation. PDE is partial derivative. Oh, why am I forgetting that simple definition? Partial derivatives. Yeah, it's partial derivatives. All right, so it's 11 o'clock. I need to head out. Live stream tomorrow, I think I know it's 11 to 12. STEM hour is going to be from 9 to 10 Wednesday, then another live stream 10 to 11. And yeah, please come out and reach out. Don't forget the exam opens this Friday, and then we'll close Sunday on the 13th. Let me know if you can't complete the exam as early as possible. So if it is an excused absence, I can kind of give you an extension. The big thing is that if you ask for extension after the 13th, the key posts, and I can't give you the extension because now all the answers are out there. All right. Thank you, JW, for showing up. Yeah, have a nice day, and I'll see you later this week.